Alright, welcome back everybody. In this video we're going to look at the examples from the antiderivatives lesson. And basically, when we're finding an antiderivative, all we're looking for is we're looking for a function that when we take the derivative of it, it gives us the differential equation that we started with. So in example 1a, I'm looking for some function that when I take the derivative of it, it gives me 3x squared minus 4x plus 8. Alright, so the antiderivative of dy dx is just going to be y. And then I have to think to myself, what do I take the derivative of that gives me 3x squared? That's x to the third. And what do I take the derivative of that gives me minus 4x? That's minus 2x squared. And what do I take the derivative of that gives me 8? That's plus 8x. And then actually I can have, any constant on the end here. This could be y equals that, or it could be this, or really anything that has those first three terms and any constant. Alright, part B, dy dx equals secant of x tangent of x. The antiderivative of dy dx is y. What, when I take the derivative of it, gives me secant of x tangent of x. Hopefully you know that that's secant of x. And then I can have, any constant on the end here. Notice this question says find n antiderivative. So any of the, infinitely many antiderivatives that I could write would be okay. Alright, let's go on to part C. An antiderivative of dy dx equals x cubed plus 5. The antiderivative of dy dx is y. What, when I take the derivative of it, gives me x to the third. That's either x to the fourth over 4 or 1/4 x to the fourth. Either way we write that, that would be fine. The antiderivative of 5 is 5x. And then, or I could have something that looks like this. Alright. Alright, part D is a little trickier. Dy dx, the antiderivative of that is y. And let's see, what can I take the derivative of that gives me 2x over x squared plus 4? Now hopefully you recognize that with this x squared plus 4 in the denominator and with an x in the numerator, this is going to be a natural logarithm based function. And so let's see, if I take natural log of the quantity x squared plus 4, the derivative of that is 1 over x squared plus 4 times the derivative of the inside. The derivative of the inside is 2x, and so we get 2x over x squared plus 4. And that is our basic antiderivative. And again, like I said, we can have any constant appended on the end there that we want. So any constant that you came up with would be fine there. Alright, part E, dy dx equals 1 over the square root of 1 minus x squared. Hopefully you recognize this as one of our rules for inverse trigonometric functions. This is the derivative of the arc sine. And so y equals arc sine of x minus 1,729. Or any constant on the end there. And then the last one here, dy dx equals e to the 2x. The antiderivative of dy dx is y. The antiderivative of e to the 2x is going to end up being 1/2 e to the 2x. And any constant appended to the end. So there is a wide variety of options there. All right, that's the end of our first example, right? Yep. Now, I talk here very briefly about the fact that there are an infinite number of antiderivatives that we could write with these different constants. And so instead, typically when we ask for an antiderivative, we're talking about the general antiderivative. When we write those, we use a capital C to represent this constant that we can have on the end, and that represents any constant. That's what's known as our constant of integration. Anytime you take a general antiderivative, you must have a constant of integration there, and that'll play very big later on in some of the concepts that we're going to deal with. So it's important that I stress it now, that anytime we take this general antiderivative, we must have our constant of integration to represent all of the infinite number of constants that are possible. All right, let's find some general antiderivatives here. Part A, dy dx equals x squared plus 12x minus 5. So the antiderivative of dy dx is y. The antiderivative of x squared is 1/3 x cubed, or x cubed over 3, whichever way you want to write it. The antiderivative of 12x, what do I take the derivative of to get 12x? That's going to be 6x squared. What do I take the derivative of to get minus 5? And then I need my constant of integration on the end. And there's my general antiderivative for that differential equation. Do the same thing in B. Antiderivative of dy dx is y. The thing that I take the derivative of to get cosine is sine. And so there's my general antiderivative in part B. Part C, let's see, this one is the arctangent. Again, if you know your derivative rules, it's a lot easier to find these antiderivatives because you'll recognize things that we take the derivative of to end up with this, for instance, because you know that derivative rule. Alright, and this part D, I've got 1/4 x to the 4th minus 5/3 x to the 3rd plus 7/2 x squared minus 11x plus c. And all I did there for every term was find something that when I took the derivative of it, it gave me what was in the original differential equation. Alright, that's the end of this video on antiderivatives. Don't forget, plus C. I always tell students this. Back in the old days, I used to take off half credit automatically on any problem where you didn't have a plus C, and some students thought that was a little bit unfair, and my reasoning behind it was, if you forgot your plus C, then you had only written one of the infinitely many antiderivatives that you were trying to represent. So I was actually being generous because you had only given me 1 over infinity part of the answer. So getting half credit was like a bonus. So whatever, I'd like to stress at the end of this video, don't forget your constants of integration. All right, have a great day, everybody. See y'all next time.